All right, we've made it to the very end of process dynamics, the mother lode here. um, and here it is. So what we want to do is we want to be able to simulate the time of response of our column as we step up our reflux ratio. So what do we mean by stepped up? Basically, every 5 seconds, we're going to step up the reflux ratio 1. And we'll simulate our X and our M's again, our molar holdups and our compositions. And then what we're going to do is we're going to create kind of our operating lines on our diagrams. This is a really fancy way of saying it. This is how they say it in this question, showing the time varying response column as the reflux ratio is increased. All that really means, right, is that we want to see how is the operation of our column restricted, or maybe lack thereof, as we increase our reflux ratio, right? So one way to think of it is that by increasing the reflux ratio, we're increasing our operating cost, right? And obviously, you know, as we increase reflux, we're cooling down more potential product, right? And recirculating that back through the distillation system. However, in theory, right, this should give us a more pure product distillate in the end, right? So, you know, if we're increasing cost or something, if you go to your boss and you say, hey, I want to increase the reflux rate on this column for a year, that could very well cost a couple, you know, maybe close to $1 million, depending on the size of the column, right? And so, if you're asking for that much money, right, you better have a pretty damn good reason that you're asking them to do that. And so this kind of analysis could give you some starting points into, hey, how am I really going to, you know, earn the will of my boss? Especially if they are a chemical engineer, they're going to be very familiar with these plots, as you'll see in your separations class if you haven't already. And this is going to be really good. This is kind of common knowledge or common language, rather, among chemical engineers. And so being able to use this as kind of robust evidence for your proposition could favor your project end, right? All that to say, to do that, you're going to be able to need to A, simulate it, and B, come up with some pretty nice looking pictures here. And so that's what we're going to do here. Easy as that. Let's come up with some nice looking pictures, right? So let's do that. First, I want to talk a little bit, though, because I can't help myself. I want to talk a little bit about the theory here of, you know, how can we really use these McCabe field diagrams. So first, what is it? It is a y versus x plot here. And what you're going to see is generally some sort of equilibrium curve. A y versus x line as well is necessary for this plot. So that's what that's going to be. And then you're going to have some sort of equilibrium curve. And obviously, for our binary distillation that we're assuming, we're going to have a 1 point and a 0, 0 connection point between the equilibrium curve, and that blue line is the y-x line. Our operating line then here is going to be some line with a slope of r over r plus 1. And it's going to come in contact with our feed line here. Right. And then finally, we'll have some sort of stripping section line that will do this. And what do these lines do? Well, here at, oops, I drew this poorly. Here at this point, we have some sort, that's the X composition of our distillate. Here at this point, it's the X composition of our bottoms product. And this is done for the more volatile component. And again, we know the slope of this line, or red line, by R over R plus 1. Now, obviously, as R increases, right, we should start to see our lines start to swing this way, right? And at maximum reflux or total reflux, where we're not producing any product, we would see this line become concurrent with our y equals x line. And that would mean we're basically obtaining the best purity possible, right? It's going right along the y equals x line, perfect, right? Similarly, our minimum reflux ratio is going to be the ratio where this line intersects the feed line at the equilibrium curve. And at that point, you know, if we drop reflux anymore, we're not going to get our desired split. So now we've kind of looked at, okay, how are these lines drawn, and how do they connect to reflux ratio? Of course, what we need to do first, though, is simulate this time response of the column over another 25-second interval as we bump up our reflux ratio. So again, here was just kind of our, I would call this our startup graph. You know, starting up the columns from whatever feed liquid we had in there to getting some sort of compositional split down the column, which is really kind of nice to look at on this left graph here. But now what we're going to go ahead and do is go ahead and do our reflux ratio bump. So what is really the way to do that here? I'm sure is the question you're all asking right now. Well, I would say that first we need to figure out what is going to be, you know, kind of our ending composition here. So what we need to figure out is, you know, as we bump reflux ratio, what are going to be our final comps in each phase. So we can relate X and Y by the relative volatility that we were given in the last section as 2. Again, these are very volatile components. They're going to be pretty easy to split by boiling point. And so how do we want to do this? Actually, I remember. X final then is just going to be the X's portion. Basically, we don't want the answer piece in there. So there we are. Actually, we just want our last column, right? So that's going to be the very last time the X's for each stage. So now that we've done that, we can go ahead and define Y final. We can just do what? X final times alpha divided by 1 minus X plus X times alpha, I think, is our Y to X ratio. Actually, these need to be our X finals, right? There we go. Because we're at Y final. And so this is going to be what is the composition at the final time, you know. And the reason we're doing that is we're using these as our steady state barometers. I probably shouldn't use the word barometer in actual term text context, but basically all it's attempting to be is, once our columns reach steady state, which it evidently has in our last simulation, what compositions are there? And these are going to kind of be the initial conditions. So let's type this out here. Y McCabe Thiele. That's going to be, we want to repeat our columns here. But how many times do we really want to do it? Should just be twice. Y final twice, right? But again, we don't want the, there we go. Yeah, do the same thing with X. For this one, we just need to row concatenate. So let's do how we want to do this. Basically, we want to separate out our condenser, our reboiler, right? But we want to repeat everything in. Yes. So everything in between repeated. Eat. Final. That 1 to -1. We want to do that twice. And then condense for the top here. So X final 0 here, and X final this would be just -1. Okay. Go ahead and set all that up. The next thing that we're going to go ahead and do is go ahead and plot out our compositions, right? So gone ahead and done that. The next thing we need to do is really figure out, what's going to happen if we bump up our reflux ratio. Well, since we went ahead and made reflux a variable in our initial right-hand side, because we knew this section was coming, it actually makes plotting this relatively easy. So all I'm going to do is t end 2 is going to be 25 more seconds, right? And res 2 should be solved by VP. We want to do our right-hand side again, but we're going to use a lambda value again for time. Lambda value for time. Vec this time though is going to be what? How do we define vec up here? We defined it as exit. So it should just be vec. Yeah, right hand side. Or rather, what's the this? Aha, found you. Okay, so then we want to do t vec and 5. There we go. What's our time span? We're going to run it from 0 to t end to, I'll mess that up. And then res 1, all the values there. Well, we want our last values, right? This is going to be our initial condition, method, equals Bordeaux, and hence output equals right. Next thing we're going to do is go ahead and grab our t-plot just like we did above. 0 to B2. Let's go with 50 points again. Let's call res 3. Let's say res 2.sol plot. And then x's, m's are just going to be np.split again. We want to split what? Res 3 twice. And our axis is going to be 0. Solid. So then big 2 equals, make subplots. Okay, and then what else do we want to do? This is basically going to be the exact same thing as above. Right? There shouldn't be just there. Oh. And I think the update layout would just keep exactly the same as without. So again, all we really did was change to 5. And thus, we have new reflux ratios. So yeah, that's that. We can see kind of the odd jar that it does. But yeah, that's that. Looks good to me. I should give you a little bit more on that actually. So again, reflux ratio is initially going to have the biggest effect on kind of our intermediate stages here, right? Again, that's our feed stage. So it's going to be a little less effective. This is the one closest to the feed stage. So it's going to be a little less effective as we go down. The curves get smoother as you get further from the feed stage. Again, we'll hold up here. Controller is doing about the same thing. And our initial disturbance returns to steady state relatively quickly. If we want to run this a little bit longer, we can see that it goes to steady state right about the 40-second mark is like really clearly steady state, right? Awesome. So now the extra fun part, which is trying to make McCabe field plots here. It actually really isn't that bad. The main thing is just making sure when we have the lines that we add the lines properly and use the right slopes and stuff, right? So let's try it. Let's try it. How are we gonna do this? Let's see. I'm gonna pause. All right, right back into this. The first thing we're gonna do is split our x's and m's. And this is a very complicated split that we're gonna go ahead and do right here. I'm gonna use res 3, and then basically not the rows, but every iterate to 16, every 16 columns. We're going to split every 2, and our axis is going to equal to 0. What's the problem? Oh, I So we went ahead and split that. Now what we want to do is make our plot. Let's start by making our plot, even though, well, no, we need to make our, we need to go ahead and draw up our lines here. Not draw up our line, my bad. Let's go ahead and get our ducks in a row in terms of our plotting lines here. So remember that we can always relate y to x by the alpha equation. So let's start with that. X plot should just be a linspace. Again, we're only going from 0 to 1 because we're in equilibrium values. Y plot then should just be X plot times alpha divided by 1 minus X plot plus X plot times. Perfect. Perfect, perfect, perfect. So let's see here. How do we want to do this piece? Big 3 equals make subplot. Here comes the tough part. So let's start with just our rows and our columns. We know we only want 1 row. We know we want 4 columns. And we know, what do we know? We know we want to name each one. I'm not going to worry about the name for right now. But we know it's going to be every 16 seconds, right? So it should be T0, 16, 32, 40. I'm not even going to try to name right now, just because this is already stretching me in terms of coding knowledge. So we're going to want to do our for loop here. So we want to do for I, X, and M in, what's our range? We want to enumerate zip. It's cool. What do we do with love? Help me out, old problem. Enumerate zip X's and M's. That's not right though, because we have to transpose them. Okay. Yes. Okay. We can do this. So then calculate y off of x, and then plot. Okay. So y equals x times alpha, again, divided by 1 minus x plus 1 times alpha plus 1, right? I really hope. So then on our next one here, what we're going to go ahead and do is take our YMC, should just be np dot repeat y 1 to the end, do that twice, xmc np dot repeat, sorry, group concatenate, and this maybe, I think this is exactly what I did already, but we're going to do it again. X0 np dot repeat x 1 to -1. I'm going to repeat that twice. Match our y's, and then put in our last value here. Okay, so let's do it. Big 3 dot add scatter. X is going to be x plot, y is going to be y plot. Load should be lines, and then this should be row equals 1, column equals I. Maybe I plus 1. I think it's I plus 1. Do it again. And x should be from 0 to 1. Y should be from 0 to 1. And then, well, actually, these probably need to be brackets. I guess. We'll see. It's one of the two. Do the parentheses or brackets. Load equals lines. And again, row equals 1, column equals I 1. And then finally, we want to add in our operating lines. Equals B, Y equals YMC. Okay, just kidding. Mode equals lines. And again, row equals 1, column equals I 1. Okay. And then just our update layout. Probably done. Awesome. Oh, so close. Okay, so we almost got it. We got our stair steps, but they are a little bit off. So the reason for that is probably I don't want this legend in here. Show legend equals false, I think. How do I get that out? Of course it wasn't. That would have been much easier. What is it? It's just show legend. Okay. Shorten this a little bit so it's a little less ugly. Ooh, I shortened it a lot bit. I just don't hate that in terms of height. Now the question is, why is our little guy off here? So, let's see. All right, so quite a while of searching, I think I finally come to the conclusion of why this plot was wrong. And it was a simple typo. This line, calculating y's as a function of x for our McCabe field calculation is actually downgrading or downshifting our McCabe field traces because that one needs to be x as we calculated y from x in every other case. So there we go. We can see our lines actually do line up within that curve. And even more so, well, that's not Nice. Zoom in the old-fashioned way here. So you can see these McCabe field plots give us a pretty good um, viewing point as to how many stages each of these is going to have. It actually doesn't have that last drop-down line, which is okay. Reason it doesn't have that last line is because of the way we calculated our stair steps, right? We didn't go through all stages, but we can see 1, 2, 3, 4, 5, and then 6th stage here is exactly what we predicted, right? Would be the amount of stages we would need. So that is our McCabe field plots. Again, this would be t equals 0. This would be t equals 16, 32, 48. If we wanted to see maybe, I don't know, every 2 seconds, you could see that. Now it's going to screw me up because of how many columns I've put in. That's okay. Maybe if we want to see how a smaller change in reflux ratio would affect our columns here, we can see that. Again, kind of cool to see the smaller changes in the boxes. Then the dramatic change that happens when we get 5, right? You see this spread happen a little bit nicer in terms of how much each stage is really carrying. But what if we did a reflux ratio of like something crazy, 100, right? What would that do to our column? Well, first off, we can see that it makes our system incredibly unstable, right? And our McCabe fields would basically break at that. So maybe that's a bit fast, but 10. Nothing too interesting here. 50. Okay, now we can see it's starting to break. And we can see that, again, here was our initial state there, and our stages start to move way down here in terms of, how much more volatile component are we getting in our product, right? Because we're increasing reflux, which means, we're getting a really pure distillate, right? But our bottom product is not so pure. That's kind of interesting to play with and mess around with. But yeah, that is modeling dynamic distillation. In my next set of videos, we're going to start to get to the controls portion of the course and figure out exactly how to control systems in chemical engineering. So start again with the tank and monitor different types of control. Talk about how we can predict stability criterion really quickly, and then simulate some more systems under control rather than right now we just have these processes running willy-nilly, right? But it's obviously our job as engineers to take the reins a little bit. So yeah, good stuff. Let's go ahead and change this reflux back down to 5. There we go. Good stuff. All right. Yeah, that's how it should look. And see you in the next one.